Okay, so we're going to get started. And the next session is our student lightning talk. And these are students who are doing the poster competition, or we're just highlighting their work. We have had a poster competition for years. I don't know when it started. It predates me and Survey. But this year we also organized on the recommendation of, I believe, Tim Glotch, a oral competition as well. So on Thursday afternoon, we'll be awarding some travel stipends to the top 3 winners in both categories. So we have just a simple slide for each one. They're going to introduce themselves, the topic, explain a little something about themselves, and move on. And we're going to be alternating virtual and in person. So here we go. We'll start with Ashley.
Hello, my name is Ashley Clendenin. I'm a physics PhD candidate at Georgia Tech, working under Dr. Tom Orlando. And my poster talk is on solar-driven in situ resource utilization on the moon, through both modeling and experimental data. So the ultimate goal of this is to look at thermal or thermochemical processing of the lunar regolith to see if we can produce some materials which are needed or, at least helpful for lunar exploration. And so some of the questions that I seek to answer are if the behavior of the simulants and the actual Apollo samples is different as they're heated, and whether producing O2 on the lunar surface with ISRU is actually feasible. So if that's something you're interested in, my poster number is 26. I'd love to talk to you. Thanks.
All right, Samra, are you there? Nope, he's not there. Alex Kanamana.
Hi, everyone. I'm Alex. I'm an incoming freshman at the University of Maryland. And the past year, I have been participating in an internship program under the mentorship of Dr. Parvathy Prim, researching lunar surface temperature modeling. So the two main science questions I sought to answer were, one, how do different methods of thermal modeling compare to each other? And two, is there a way of representing results of thermal modeling in the form of a mathematical expression? And so these questions are important for future applications of thermal modeling, for example, volatile simulations or interpreting emission spectrums. And I believe my results are promising for immediate implementation in these future applications, as well as for a future understanding of the thermophysical properties behind the results. So my poster number is 4. And yeah, just come check it out. Thank you.
Do we have a kill? Usually this works really well. This year, not so well. No? Okay. We'll move on. We'll try and catch some people towards the end. Kaylin Kanamana.
All right, good morning, everyone. My name is Kaylin Gallinger. I'm a PhD candidate in geophysics at the University of Western Ontario, working with Dr. Catherine Niche. And my poster is on ground truthing multi-wavelength radar and thermal infrared remote sensing measurements at the Surveyor 7 landing site. Now, as we know, one of the main benefits of returning to the moon over the next few years will be the opportunity to visit sites and collect samples that were not possible during the Apollo era. And one of the key of these sites that was identified in the recent decadal survey are impact melts around Copernican craters, as these can fill in a gap in our understanding of the lunar chronology that's not sufficiently covered with current samples. My work is looking to get a head start on this by looking to the past, and specifically the landing site of the Surveyor 7 spacecraft, which landed on the northern ejecta of Tycho in 1968. I'm making use of newly digitized images from the University of Arizona's Lunar and Planetary Laboratory from Surveyor 7's television camera, and trying to relate these to remote sensing observations in both radar wavelengths and thermal infrared using models and various observations to hopefully demonstrate a quantitative link between these that we can then apply to studying all craters and other high density and thermal inertia regions on the moon. So if you're interested, come talk to me this evening or at the virtual poster session tomorrow. Thank you very much.
Hi, I'm Catherine Gansler. I go by Katie. I'm a pre-candidate for my PhD program at the University of Maryland, working with Nick Schmer. And I study gravimetry of smaller features on the moon and Mars. Specifically right now, I'm using Curiosity rover's inertial measurement unit, which is basically an accelerometer as a gravimeter, but you'll have to wait to see results from that probably next year. What I'm presenting this year is an analysis of Grail lunar data to test the limits of what we can, of the size of small objects that we can detect. So if you're thinking about using orbital gravimetry using orbital gravimetry to look for lava tubes or other maybe kilometer scale objects on the surface or shallow subsurface of the moon, we took a look at sinuous rills as a test case for possibly looking for lava tubes, but you might want to check out our results before getting in too deep on looking at those smaller features using gravity. Thanks.
Hello, everyone. My name is Jacob Giles, and I'm a master's student at the University of Maryland. My poster focuses on imaging the shallow subsurface for lunar analog exploration using surface waves. Our study focuses around SP crater in the San Francisco volcanic field and shares many similarities with the lunar surface, making it an ideal lunar analog. You may be wondering, why use surface waves instead of body waves? Surface waves present advantages over body waves as they are always generated in active surveys, have the strongest energies, and maintain the highest resolution in the near surface. Our analyses focus around using multi-channel surface wave analysis that can use the dispersive nature of surface waves to understand the velocity structure at depth. Seismic data can aid in the understanding of volcanic field formation in like planetary environments and can enable the can broaden our capabilities for lunar exploration as we make our way back to the moon. Thank you for your time, and I look forward to speaking with you on more at poster number 55.
Okay, virtual, go ahead.
All right. Hey, everyone. My name is Haley Chetna. I'm a doctoral student at the Department of Geological Sciences at the University of Colorado Boulder as of fall of 2022. Working together with my research advisors and collaborators, Dr. Kelsey Singer at Southwest Research Institute here in Boulder and Dr. Carolyn Crow at CA Boulder, we introduced in our poster presentation the ejected transport model we are currently developing to understand the contribution of distal impact ejecta fragments in redistribution of material around the moon. As part of my dissertation work focused on impact and ejecta physics and processes across the solar system. So we know when we have an impactor striking a body to excavate a primary crater, large amounts of surface materials are ejected up to global distances away from the crater interior. Deposition of these distal ejecta could potentially introduce an exotic component that could potentially skew age interpretations if not accounted for. Therefore, to provide a context to lunar sample analysis in the future, our project goal is to develop a comprehensive analytical model that provides information about the impact history and potential processes that can be operated in a given area through time. And here we particularly focus on tracking ejecta and secondary craters as a way to constrain where impact ejecta influence bodies. Please check out our posters, and thank you guys. And that is poster number 77. Thanks.
Hello, good morning, everyone. I'm very excited to be here. My name is Anna Narvaza, and I'm a master's student at San Diego State University studying civil and environmental engineering. And for my poster presentation, my poster overviews my research on investigating the response of different lunar construction materials, specifically for launching and landing pads, to the different extreme temperature variations happening on the moon. So the three distinct construction methods were utilized in this project, which includes enhancing the regular simulant LHS-1 with xanthan gum biopolymer, implementing cold isostatic pressing and spark plasma sintering. And with fabrication, after fabrication, we put them through thermal cycling using an oven and liquid nitrogen to simulate lunar day and nighttime. And to get our results, we used unconfined compression test and SEM analysis to examine the evolution of the specimens, micro and macro structure. And so it's an important topic right now because it's we get to look into the idea of the resilience and durability of the materials we'll be using to build on the moon. And so if any of these are sounds interesting and would like to see my results and findings, please visit my poster at number 7, and I'll be more than happy to discuss it with you and also learn from you too. Thank you.
Hi, everyone. My name is Jared Roletta, a fourth-year physics major at St. Mary's College of California. If you've ever brought an instrument into the field, then you know the headache of carrying around a bulky laptop with a nest of wires in your bag just to record data. Or you've experienced difficulty viewing your screens in harsh sunlight conditions. Or worst of all, you've lost power to one or more key components of your apparatus due to the lack of electricity in the field. What if I told you there were one device that can circumvent all of these issues? Meet X-Rise. X-Rise not only does so, but it's designed to give the user live, real-time instrument data interpretation and visualization. And although X-Rise was designed for specific use in tandem with an XRF in the Kilbourne Hole deserts of New Mexico, this system can be adapted to work across a multitude of different scientific instruments and work across a variety of different environments. And we hope someday soon, even the moon. Thank you.
Hi, everyone. My name is Lorraine Rosselló del Valle, and I'm at the University of Central Florida, and my advisors are Dr. Christopher Bennett and Dr. Carrie Donaldson-Hanna. I am working on SWEEPS, or the Space Weathering Environment for Exploring Planetary Surfaces. It is a simulated environment chamber capable of simulating conditions from Mercury all the way to Pluto. And we have conducted 3 preliminary experiments, 2 with the UV source and 1 with the electron gun. With the UV source, we have irradiated an aliquot of St. Carlos olivine and an aliquot of CI simulant from Exolith Labs for a total of 41 hours. And with the electron gun, we have bombarded an aliquot of St. Carlos olivine with 2 keV electrons for a total of 11 hours. We have collected bidirectional reflectance spectra in the mid-infrared, diffuse reflectance spectra in the visible to near infrared, as well as quadrupole mass spectroscopy data. We present our results at poster 72, and I look forward to seeing you there. Thank you.
Hello, everyone. I'm Virginia Sacchi. I'm from Florence, Italy. I'm a rising senior at Embry-Riddle Aeronautical University. I first started working on the lunar exosphere with my undergrad advisor, Dr. Edwin Merkowitz, and I'm currently expanding on this research with my mentors, Dr. Manel Sorrentos from the Heliophysics Division at NASA Goddard Space Flight Center. And I'm also working with Dr. Donna Kruprachi from the Solar System Exploration Division. I'm currently focusing on velocity trends and altitude variations of sodium emissions in the lunar exosphere, in particular by analyzing how line centers and line widths of these emissions change as we approach and move away from a full moon and as we step out in altitude. I plan on getting a better understanding of dawn-dusk asymmetry that was previously found and set new constraints to current models that are being used in the field. Although most of the research so far has been in data processing and data analysis, I plan on getting more involved in the modeling too, as I'm particularly interested in the theoretical aspect of my research project in particular, but of physics in general. If you would like to hear more about my poster, please come by poster 63, and I'll be happy to answer any of your questions.
Hello, I think I am perfectly audible. I am Trinesh Shana from Physical Research Laboratory, Ahmedabad, India. I am working under Sanjay Kumar Mishra. So we know that a complex plasma environment around moon is connected due to the dynamic interaction between solar UV radiation and the solar wind plasma collection. So in the day side of the moon, due to dominant UV induced photoemission, a photoelectron sheath is created around the vicinity of the sunlit moon. And we have studied the distribution of the photoelectrons, which is emitted from the lunar surface. And our theoretical study suggests that it is highly dependent on whatever the incoming solar flux coming from the sun, as well as material properties like work function, quantum yield. Also, we have found that the distribution is highly depends on the positive lunar surface potential. So if you want to know more about this, please visit the poster number 66. Thank you for your time.
Hello, everyone. My name is Cosmo Sykes, and I'm a PhD student at the University of Maryland. My advisors are Jessica Sunshine and Megan Newcomb. So I'm studying a compositionally unique pyroclastic deposit on the lunar near side. This deposit is called the Sinus Astum Dark Mantle Deposit, and it covers an area roughly the size of Wisconsin. So what's unique about this deposit is there are unusual spectral signatures, which have been interpreted to represent an unusually high abundance of the mineral spinel. These signatures are observed only in this dark mantle deposit and nowhere else on the moon. So I'm using a combination of remote sensing and petrological experiments to study the origin of this unique deposit. If you have any questions or would like to chat, please come find me at my poster. I'm number 71. Thank you.
Okay, and now Kendall, are you there?
Yep, I'm here.
Okay, great.
All right, so I'm Kendall. I am a researcher from Lowell Observatory in Flagstaff, Arizona, and we've been developing a rapid multi-angular photogoniometer that we use for analyzing planetary surface samples. And so what we have is we've got this 3D printed dome that's been painted black on the inside that has these reflective lines at known angles of incidence, or azimuths, I'm sorry. And then we've got this array of LEDs at known angles of incidence that when shined onto a sample that's being analyzed through a small aperture in the bottom, the light reflects off the sample and into these reflective lines. And we've got a camera sensor that can image the lines, and it effectively acts as an array of tiny sensors. And so we can average together these like little boxes of pixel data together to produce these data sets that we could then send through an interpolation routine to produce these multi-angular reflective maps. If you have any questions, feel free to email me. I have COVID, so I can't actually be down on the floor.
Thank you. And can we go back to DTN? Is it the next one? Okay. No, to Adityan. I think it was the one I had. There we go. Yep.
Hello, my name is Adi Swaminathan. I'm a rising senior at Tenafly High School in New Jersey. Our co-authors are fellow students from Tenafly High School, as well as our mentor, Dr. Jeff Pleshaw from the Johns Hopkins University Applied Physics Lab and the University of Maryland. Great thanks to the XMAS program for giving us this opportunity. So our research focused on the differences in the composition of the lunar maria and highlands, and we were able to draw insights into the lava and the magma which formed the maria and the highlands by analyzing linear regressions of pairs of mineral abundances from craters on the moon. If you would like to see the mathematical beauty on the moon, please come visit our poster number 21.
Okay, we're skipping, and there we go, McKinley. Oh, yeah, we're skipping Belleville. They weren't able to come. And McKinley, come on up.
My name is Jovan Champ. I'm a McKinley Technology High School graduate going through the computer science STEM track. I'm going to University of Hartford in Connecticut for computer science.
Good morning. My name is Josiah Smith, and I graduated from McKinley Tech in the computer science track. I'm attending Towson University in the fall.
And I'm Hannah Floyd. I just finished my sophomore year at McKinley Tech and I'm on the computer science track.
We are representing a group of 9 students for the Great Lunar Expedition for Everyone, or GLEE.
GLEE is a mission to the surface of the moon where we will be conducting science and testing technology with hundreds of 5-gram lunasats.
Our team is in charge of developing the Arduino code for the Lunasat, and we can't wait to tell you more at our poster later today.
Thank you.
Nope. The other way. We're looking for logos. Yeah, I know. I not use them. There we go. Good job. Go on.
Hi, everyone. My name is Asa Nelson, and I am in 7th grade, and I'm from Logos Public Charter School in Medford, Oregon. The title of our study is 12 New Candidate Senior Rules on the Moon. Our goal is to identify new senior rules on the far side of the moon with similar features to the ones found on the near side. Using LROC Quick Map, we mapped 12 new features on the far side with similar characteristics to the senior rules on the near side. We like to have these features considered as new senior rules. This is notable because there are very few senior rules documented on the far side. Also, be really cool to name them. Please come and see our poster and share your thoughts with us at poster location 20. Thank you.
Okay, we are going back to Samrat. Are you there?
Yeah.
Okay, go ahead.
Hello all. Allow me to introduce myself. I am B. Samrat, and an enthusiastic undergraduate student, and I am joined by my esteemed co-author, Professor Dr. Arun PV from IIIT Sri City. Together, we are on an inspiring journey working on groundbreaking ISRO project focused on Chandrayaan-2 lunar data from the IARS instrument. Our passion lies in exploring the mysteries of space and specifically the lunar surface. Chandrayaan-2 has provided us with a wealth of data that holds immense potential for understanding the geology and mineral composition on the moon. But what makes our research truly thrilling is how we use advanced machine learning techniques to uncover the secrets hidden in this lunar mineral data. Lunar data exploration matters for the future space missions, resource exploitation, and planetary exploration across our solar system and beyond. Using cutting-edge deep learning techniques such as graph-based neural networks, we transform latent space features extracted from the lunar hyperspectral image into graphs. These graphs enable us to better understand the spatial and the spectral relationships on the lunar surface. The potential of using these approaches extends to studying other planets, stars, and other bodies through the universe. But here, what sets us apart, our research is designed to be accessible to all, regardless of your background in machine learning. We aim to make complex topics simple and engaging so everyone can join the journey of exploring space. Where you have a passion for astronomy, technology, or simply a curious mind, our poster session promises to be fascinating experience. Join us at poster number 34. Thank you for your attention, and we are looking forward to meeting and discussing our research with each and every one of you. Thank you.
Thank you. Rivamo. Okay, Akhil.
Hello, everyone. I'm Akhil Gala, currently in my senior year at Indian Institute of Information Technology, Sri City. My co-author is my fellow professor at the same college, Dr. Arun. Today, I'm here to talk about mineral mapping of lunar surface using the data from IRS spectrometer on board Chandrayaan-2 satellite. We use hyperspectral data and classify each pixel to its end member mineral using machine learning techniques integrated with graph-based strategies such as graph convolution networks. The reason for employing graph-based methods is easy interpretability of node embeddings and explainability of the final classification result. We used efficient graph formulation techniques to capture spatial and spectral relations between pixels, which play a major role in final classification. If you want to discuss more, you can find me at poster number 38. Thank you, everyone.
I would like to thank all of our lightning talk speakers. You all did very well.